welcome back to our deep dive into number theory.
Yeah. Always fun to go deeper on this stuff.
Today we're tackling mathematical induction,
Yeah.
which is a really powerful tool for proving statements about natural numbers.
It's kind of like a master key, for unlocking all these truths about infinite sequences.
I like that, the master key. Okay.
Yeah.
And it can be a little bit intimidating at first.
It can seem that way, but the underlying logic is very elegant.
Okay.
And even fun, I'd say.
You had me at fun math.
All right.
So one of the things that really helped me when I was reading through some of the material that you sent over was the domino analogy.
Right.
Can you kind of explain that a bit more for our listeners?
Sure. So picture a line of dominoes, set up perfectly.
Mm-hmm.
And, if you knock over the first one, it'll trigger this chain reaction and topple all the others.
Yeah.
Mathematical induction works in a similar way.
Okay. I see the connection there, but how do we apply this to actual numbers and proofs?
So it's a two-step process. First, we prove that our statement is true for what's called the base case,
Okay.
which is usually the smallest value, like n equals 1.
Okay.
This is like making sure that first domino falls.
I see. So why not test like the fifth domino or something, just to be extra sure?
Well, we choose the smallest value because it's our starting point.
Okay.
If we can prove the statement holds true for that very first case, it sets the stage for that chain reaction.
Okay, so it's not about just checking random dominoes. It's about making sure that the very first one is going to fall.
Exactly. And then the second step is called the induction step. And this is where the real magic happens.
Ooh. Okay.
We assume our statement, let's call it P of k, is true for some arbitrary natural number k.
Okay.
This is called the induction hypothesis.
Okay, so we're basically just saying, let's pretend like this one domino in the line has already fallen.
Precisely. And then we use this assumption to prove that the next domino P of k plus 1 must also fall.
Okay.
So we demonstrate that if one case is true, the next one must also be true.
So it's like a chain reaction of truth.
Yes.
Starting from that very first domino,
Yeah.
extending out infinitely.
You got it. And this chain reaction is what makes mathematical induction so powerful.
Okay, this is really cool. I'm already my mind is a little bit blown.
Good.
But before we get into some specific examples, can you give us a little sense of the historical context? Like, when did mathematicians start using this technique?
Well, the journey of mathematical induction actually spans centuries.
Wow.
With contributions from, brilliant minds across the globe.
Mm.
The formal method that we use today that evolved gradually.
Okay.
But there are traces of inductive reasoning that go surprisingly far back.
Yeah, I read somewhere that there might even be hints of it in Plato's work.
That's right. Some scholars suggest that Plato's Parmenides, which was written around 370 BC, might contain early implicit forms of inductive thinking.
Wow.
Of course, it wasn't the rigorous system that we have now, but it's fascinating to see these early seeds of the idea,
Yeah, definitely.
being planted so long ago.
So who are some of the key players that really helped to kind of develop this technique?
So around 1000 AD, the Persian mathematician Al-Karaji, he used a form of induction to prove things about arithmetic sequences, which are lists where each number is the previous one plus a constant difference, so like 2, 4, 6, 8. And even on Pascal's triangle, that pyramid of numbers you might have seen with patterns and combinations.
Yeah, it's really incredible how these mathematicians were working with such complex ideas centuries ago.
It is then in the 16th century, we have Francesco Maurolico, who used an inductive-like approach to prove a theorem about the sum of odd integers.
Wow.
Now, he didn't explicitly state the induction hypothesis as we know it today, but the logic was clearly there.
So it's like watching the pieces of the puzzle come together over time.
Exactly. And the puzzle was further assembled in the 17th century with Blaise Pascal, who gave us a more explicit formulation of induction.
I see.
But it was in the 19th century with the rise of modern logic that mathematical induction was truly formalized.
Okay, so who are some of the big names in that final push towards formalization?
So thinkers like George Boole, Augustus de Morgan, Charles Sanders Peirce.
Wow, big names.
Yeah, they were instrumental in refining induction into this powerful, precise tool we use today.
Okay.
And of course, we can't forget Giuseppe Peano, who went so far as to include an axiom of induction in his famous Peano axioms.
Wow.
Which rigorously define the natural numbers.
So we've got this rich history, but I'm ready to see mathematical induction in action.
Okay.
Can we dive into an example?
Absolutely.
I know from the sources you provided that the proof about the sum of the first n odd integers being equal to n squared often trips people up?
It's a classic example. It perfectly illustrates the power of induction.
Okay.
So let's break it down together.
Right, let's do it.
Okay. So our statement, P of n, claims that the sum of the first n odd integers is equal to n squared.
Okay.
In other words, 1 plus 3 plus 5 and so on, up to 2n minus 1 equals n squared. So 2n minus 1, that represents the nth odd number.
Okay, so just to clarify, we're basically trying to prove that adding up a sequence of odd numbers will always give you a perfect square.
Yes.
That's a pretty neat pattern.
It is.
Okay, so how do we apply induction to this?
So first the base case.
Okay.
Let's test for n equals 1.
Okay.
On the left side of the equation, we simply have 1, which is also equal to 1 squared.
Right.
So P of 1 holds true. Our first domino is fallen.
Awesome. Okay, so that seems pretty straightforward.
Yes.
What about the induction step?
Okay, so now we assume P of k is true for some arbitrary natural number k.
Okay.
So that means we're assuming 1 plus 3 plus 5 all the way up to 2k minus 1 equals k squared.
Okay.
Now remember, this is our induction hypothesis. We haven't proven it yet, but we're assuming it's true for the sake of the proof.
Right. So like we were saying before, it's like we're pretending domino number k has already been knocked over.
Exactly. And now our goal is to use this assumption to prove that P of k plus 1 must also be true. We need to show that adding the next odd number to the sequence, which is 2 times the quantity k plus 1 minus 1, will result in the quantity k plus 1 squared.
Okay, so if we're saying that the sum of the first k odd numbers is k squared,
right,
then adding that next odd number should give us the quantity k plus 1 squared.
Yes.
Okay, I'm very curious to see how this plays out.
All right, well, let's use our induction hypothesis.
Okay.
We can replace the 1 plus 3 plus 5 up to 2k minus 1 part of our equation with k squared.
Okay.
This gives us k squared plus 2 times the quantity k plus 1 minus 1 on the left side.
Okay.
Now let's simplify.
All right, so we've got k squared plus 2k plus 2 minus 1, which simplifies to k squared plus 2k plus 1.
Yes.
Wait a minute, that's just the quantity k plus 1 squared.
You got it?
Oh, wow.
By assuming P of k is true, we've shown that P of k plus 1 must also be true.
Okay.
We've demonstrated that if one domino falls, the next one must fall as well.
That's so elegant.
It is.
So to recap, we established our base case.
Right.
And we've shown that the truth of any case implies the truth of the next case.
Correct.
Does that mean we're done?
Yes. By the principle of mathematical induction, we've now proven that the sum of the first n odd integers equals n squared for all natural numbers.
Wow, that's powerful. And this isn't just about odd numbers, right?
Yeah.
Induction lets us prove formulas about any pattern that changes predictably as n increases.
Right.
Like I said before, it's like having a master key for these infinite sequences.
I couldn't have said it better myself.
Okay, so the sources that you sent also mentioned something called strong induction.
Yes.
How is that different from the type of induction we just discussed?
So strong induction, also known as complete induction, is like regular induction, but with a more powerful assumption in the induction step. Instead of assuming just P of k is true, we assume that P of n is true for all natural numbers less than k plus 1.
Whoa, wait a minute. I thought we were only assuming one case was true. This changes everything.
It does. It's much more powerful.
This suddenly feels way more powerful.
Imagine you're trying to factor a huge number.
Okay.
Strong induction lets us break it down knowing all its smaller parts are already pre-factored, so to speak, making the job easier.
So hold on, it's not just proving formulas. It's like a way to break down any problem into smaller, already solved pieces.
Precisely.
That's amazing.
It provides a very powerful framework for tackling more complex problems.
Wow.
Where the truth of a statement depends on the truth of multiple preceding cases.
Okay, so induction is clearly powerful in pure math.
Yes.
I'm wondering, though, do we ever actually use this kind of thinking in everyday life?
That's a great question.
Yeah.
So while we might not always be consciously using mathematical induction in our daily lives, the underlying logic of starting with a base case and building a chain of reasoning is very common.
Can you give us an example?
Certainly imagine you're troubleshooting a computer program.
Okay. Yeah.
You might start by checking the most basic things. Is it plugged in? Is the software up to date? And then you systematically work your way through more complex possibilities, relying on the fact that each previous step has been verified.
So it's like starting with the simplest explanation and then building upon it step by step.
Exactly. However, it's important to note that this type of reasoning, while similar to mathematical induction, isn't quite the same.
Okay.
In everyday life, we often use inductive reasoning,
Okay.
which involves drawing general conclusions from specific observations.
Okay, so what's the difference then between inductive reasoning and the mathematical induction we've been talking about?
So inductive reasoning, while useful, doesn't offer that same level of certainty as mathematical induction.
Gotcha.
With inductive reasoning, no matter how much evidence you gather, there's always a chance your conclusion could be wrong.
Okay.
A classic example is the pattern of sunrise.
Okay.
We observe the sun rising every day,
Right.
so we inductively conclude that it will rise again tomorrow. But this conclusion is based on past observations, not on some fundamental guarantee.
I see. So it's about probability versus like absolute certainty.
Exactly.
Okay.
Mathematical induction, on the other hand, gives us a way to establish truth with 100% certainty
Okay.
within a system of mathematics. It's not about likelihood, it's about proving something true beyond any doubt.
That's a powerful distinction. It makes me appreciate even more the rigor and the elegance of mathematical induction.
It is elegant.
It's like having a mathematical superpower for uncovering and proving these truths about infinite sets.
I agree. It's a testament to the beauty and power of mathematics itself.
Yeah.
The ability to take these complex patterns, these complex ideas, and break them down into these elegant logical structures.
This has been a fantastic deep dive. I'm amazed by how much depth and richness there is to this concept of mathematical induction.
There is a lot to it.
I'm glad we got to spend some time with it today.
Me too.
So for our listener who are ready to kind of explore further,
Yes.
I know you had a recommendation for us.
I highly recommend the book Concrete Mathematics by Graham Nuth and Potashnik.
That's a classic.
It's a classic text that really illustrates how induction and other discrete math concepts underpin so many areas of computer science and mathematics.
It's amazing how foundational some of these concepts really are.
It is.
So as we wrap up our deep dive into mathematical induction, any final thoughts for our listeners?
You know, I would encourage everyone to not just learn about induction, but to play with it, experiment with it.
Yep.
See if you can spot inductive arguments in your everyday life, in the news and conversations.
Yeah.
It's amazing how often this powerful mathematical tool subtly shapes our thinking.
I love that challenge. It's like a mental treasure hunt looking for the hidden logic of induction all around us. So until next time, thanks for joining us for this deep dive into the world of number theory. Keep exploring. Keep those minds curious. And remember, sometimes the most complex patterns can be understood with a simple chain reaction of truth.